Okay, let's talk about something we all do every single day, but probably never really think about. What happens to water after it goes down the drain? Well, it's not just water anymore, is it? It becomes this complex cocktail of everything we use and discard, a hidden story in every single drop.
So think of this as an investigation. We're going to be detectives taking a deep dive into the microscopic world of wastewater. Our mission? To learn how to decode the clues it holds. And trust me, these clues reveal so much about the health of our communities and even our planet.
All right, here's our game plan. First, we'll get the big picture on water's hidden story. Then, we'll check out the physical clues, sight and smell. After that, we'll dive into the invisible chemical ingredients, run the all-important oxygen demand test, and then uncover the unseen biological dangers. Finally, we'll put it all together to see why this decoding business really matters.
So, let's kick things off with the big question. Why should we even care what's in our wastewater? Well, because it's a direct reflection of us, of our lives, our industries, our health. It's this incredibly complex mix of everything we flush away, and all of it all has an impact.
Let's break down our four main suspects here. First up, you've got pathogens. These are the microscopic bugs that spread disease. Then there are suspended solids. This is the stuff that causes all that nasty sludge. Next, biodegradable organics, which literally suck the oxygen, the very life, right out of rivers. And finally, nutrients, which act like a super fertilizer for those huge toxic algae blooms. Every single one is a silent threat.
Every good detective starts with what's right in front of them, right? The obvious evidence. And in our case, that means using our senses. What does the water look like? What does it smell like? These are the very first clues to its story. And just look at this transformation from fresh to septic. Fresh wastewater is, well, it's gray, it's murky, and it has a generally disagreeable smell. But as bacteria get to work and use up all the available oxygen, it turns black and starts to give off that unmistakable rotten egg smell. Yeah, that is the smell of decay.
Now, temperature. Think of temperature as the gas pedal in this whole process. Wastewater is almost always warmer than fresh water, which creates this perfect, cozy breeding ground for microbes. The warmer it is, the faster the decay, which just perfectly sets the stage for our next set of clues.
Okay, it's time to bring out the forensics kit. We're moving beyond what we can see and smell. Now we're dusting for chemical fingerprints, those invisible clues that tell us exactly what's in the water and even how old that contamination is.
So if you could magically boil off all the water from a sample, this is what you'd have left over. It's about half organic. We're talking food scraps, human waste, that kind of stuff. The other half is inorganic, things like sand, grit, and salts. Knowing this difference is absolutely crucial for designing the right treatment plan.
So how do we actually separate all these different solids? It's a pretty simple three-step process, really. First, you evaporate a sample to find the total amount of solids. Then you filter another sample to catch everything that's just suspended in the water. And finally, you let a third sample just sit for a couple hours to see what settles to the bottom. It's methodical, but it tells us so much.
Nitrogen tells a fascinating story. The form that it's in acts like a chemical clock, revealing the pollution's age. In fresh waste, you find one type of nitrogen. As it decomposes, it changes form, first to ammonia, then to nitrites, and finally to stable nitrates. Each stage is like a new chapter in the story of decay.
Every good investigation has a smoking gun, and in the world of wastewater, that smoking gun is a test called biochemical oxygen demand, or just BOD for short. This is how we measure the true extent of the pollution.
So, what exactly is BOD? Okay, think of all that organic waste as a giant all-you-can-eat buffet for microorganisms. The BOD is simply a measurement of how much oxygen those tiny creatures need to breathe while they're gobbling up that entire buffet. The bigger the feast, the more oxygen they have to consume.
And it's a pretty simple equation, really. More pollution means more food for microbes. More microbes means more oxygen consumption, which means a higher BOD. And here's why that's so dangerous. When water with a high BOD gets into a river, it can suck all the oxygen right out of it, creating dead zones where fish and other aquatic life just can't survive.
All right, now we're going undercover. We're getting out the microscope and diving into the world of invisible suspects. And these are the dangers that pose a direct threat to our health. This is where the investigation gets really serious.
So meet the invisible criminals of our story, pathogens. These are the bacteria and viruses that make us sick. They essentially hitch a ride in our wastewater, coming from people who are already infected, and if we're not careful, they can spread like wildfire.
And this threat is very, very real. Untreated wastewater can spread deadly diseases like typhoid, cholera, and dysentery. For so many people around the world, clean, treated water isn't a luxury. It's truly a matter of life and death.
Now, hunting down every single specific pathogen is pretty much impossible. It's way too time-consuming and difficult. So scientists use a clever trick. They look for a common, mostly harmless group of bacteria called coliforms. If they find coliforms, they know the water has been contaminated with feces, which means the really dangerous pathogens could also be present. It's an indicator.
So, we've examined the physical evidence, we've dusted for the chemical prints, and we've identified the microscopic suspects. Now it's time to put it all together and crack the case. What's the final verdict?
You see, all of this detective work, it all has one single, vital purpose. Every clue we've uncovered, from the water's color to its BOD to the number of coliforms, gives engineers the exact information they need to design treatment systems that will actually work. This is how we protect public health and how we protect our environment.
So we have the tools. We have the ability to read the stories hidden in our water. We can decode its secrets and understand its warnings. The real question is, are we listening? Are we ready to act on what we know to protect our future?